All right, picture this. You've got these two tiny particles, right? And they're light years apart. But somehow, they're moving in perfect sync, like they're connected by some invisible thread.
It's pretty wild, right? That's quantum entanglement.
And get this, scientists just saw it happening in quarks. You know, those fundamental particles that make up, well, pretty much everything.
It's a big deal.
Big time. We're diving deep into a new paper from Nature Journal. They're talking about this huge discovery at the Large Hadron Collider. Researchers actually observed this spooky action at a distance in top quarks, the heaviest quarks there are.
It's a game changer.
So before we get lost in the quantum weeds, let's do a quick recap. Quarks, they're like the teeny tiny Legos that make up protons and neutrons, the building blocks of matter.
Right, and the Large Hadron Collider. Think of it as our superpowered microscope. It smashes protons together at almost the speed of light so we can see what's inside.
It's like smashing a couple of watches together to figure out how they work, except on a much, much smaller scale.
And way more chaotic. That's the amazing part. The LHC is like this chaotic mosh pit of particles constantly colliding. To actually see entanglement in that environment, it's like trying to hear a whisper at a rock concert.
So how did they do it? Seriously, trying to find evidence of entanglement in the middle of all that chaos sounds nearly impossible.
It's incredibly impressive. They looked at millions of pairs of these top quarks along with their antimatter opposites, the anti-top quarks, paying close attention to something called spin.
Spin?
Yeah, like a tiny compass needle inside each quark. It can point up or down.
Gotcha. Each quark has this little internal compass. Okay, I'm with you. So what did they find?
They found that the spins of these entangled pairs, they weren't random, they were linked. Like those tiny compasses were magnetically connected, always pointing in the same direction. That's the signature of entanglement. Normal physics can't really explain that spooky action at a distance, but it's right there in the standard model of particle physics, which predicted it for these heavy particles.
So they were expecting to see entanglement even in all that LHC madness.
Kind of, yeah. The theory was there. But seeing it, actually observing it happening in these incredibly short-lived particles, it's one thing to say, hey, I think this rare flower can bloom in the desert. It's a whole other thing to see it blooming with your own eyes.
No kidding. It's one thing to talk about it and another thing to see it. It really shows how mind-boggling quantum mechanics can be.
Absolutely. The fact that they could do this with top quarks makes it even more incredible.
Because they're so unstable, right?
Exactly. Top quarks are like tiny little fireworks, existing for just a fraction of a second before they decay into other particles.
So how could they even measure the spin if the quarks disappear so quickly?
That's the really clever part. They had to study the decay products, those particles that are left behind, to figure out the initial state of the top quarks.
So they're like cosmic detectives dusting for fingerprints, except their fingerprints are these almost invisible particles.
Exactly. And from these tiny clues, they can reconstruct what happened during the collision, revealing the entangled state of those original top quarks. They found that certain combinations of particles, those fingerprints you mentioned, appeared way more often than they should have if the quarks weren't entangled.
That's some seriously impressive detective work. But how do you go from seeing a suspicious fingerprint to knowing definitively that those top quarks were actually entangled?
Great question. They use something called the D parameter. It basically measures how much the spins of those two top quarks are correlated. For entanglement to be confirmed, the theory said D had to be less than 9^1/3.
So if D is above -1/3, no entanglement if it's below.
Lungo. Think of it like a scoreboard. They needed to hit a certain score for entanglement to be legit.
All right, what was the score? Did they make it?
You crushed it. ATLS got a 9 at 0.537, and CMS got a 9 at 0.480. Way, way beyond that 9^1/3 threshold. Those numbers, they were like a seismic event in the world of particle physics.
Wow. No question about it then. Entanglement confirmed.
Absolutely. And you know what makes this even cooler? Most entanglement studies, they've been done in these really controlled lab settings, like with photons or atoms, cooled down to almost absolute zero.
Because quantum stuff is easier to see when it's not overwhelmed by the noise of the universe.
Exactly. It was almost an article of faith that to study something as delicate as entanglement, you needed those pristine, isolated systems. But this LHC discovery, it flips the script.
So you're saying the LHC, this chaotic particle mosh pit, is actually the perfect place to study entanglement.
It seems crazy, right? But that's what it's looking like. This opens up a whole new world for studying entanglement in high-energy environments. We're talking about probing the quantum world under the most extreme conditions imaginable.
That's wild. Okay, so what does this mean? What are we going to do with this information? Why is studying entanglement at the LHC such a big deal?
Well, for one, it could allow us to study entanglement in other heavy particles that we can create at the LHC, particles that we thought were just too difficult to analyze in this way before.
You mean like the Higgs boson, the one that gives mass to all the other particles?
The one and only. Imagine seeing entanglement in the Higgs boson, the particle that underpins the very fabric of our universe.
Okay, now that's what I'm talking about.
It's like getting a new pair of glasses to see the quantum world, a way to see its mysteries with incredible clarity and precision.
This is huge. But let's bring it back down to Earth for a minute. Why does this matter for those of us who don't spend our days smashing particles together? Why should we care about entangled quarks in a giant collider? It's cool, don't get me wrong, but how does it affect our everyday lives?
That's the million-dollar question, right? I mean, it seems like something straight out of Star Trek, something only a physicist could love, but the implications go way deeper than that.
All right, I'm listening. Tell me more. Why is this such a big deal?
Because it challenges everything we thought we knew about reality. Entanglement suggests a level of connection that just seems impossible according to the physics we experience in our everyday lives.
You're talking about spooky action at a distance, right? Where two particles are connected no matter how far apart they are.
Exactly. It's something that even Einstein struggled to wrap his head around. But here it is, right in front of us. We're seeing evidence for it in the most fundamental building blocks of the universe.
So what does this all mean? What are the possibilities? It really makes you think, if something as tiny as a quark can be linked like that across such huge distances, what does that mean for, I don't know, for everything? Could there be connections we just haven't even drummed up yet? Stuff that connects the smallest things to the biggest things in the universe?
It's a pretty amazing thought, and the really exciting part is that it's not just theoretical anymore. This discovery could lead to some really groundbreaking tech in the future. Imagine using entanglement for things like quantum computing or even communication.
Okay, now you're speaking my language.
We could be talking about networks that are impossible to hack, or computers so powerful they could solve problems in seconds that would take normal computers billions of years.
Sign me up. Super fast computers, unbreakable codes. That sounds like we're living in a sci-fi movie.
We might be closer than we think. But even if those applications are a long way off, just being able to study entanglement at these crazy high energies in these chaotic environments, it's a game changer. It's like we've stumbled onto a whole new playground for quantum physics, and who knows what we'll discover out there.
This whole thing has been a wild ride. We started with these tiny particles moving in sync and somehow ended up talking of the very fabric of reality and the future of technology. Amazing to think that something as weird and mysterious as quantum entanglement could be so important.
It just shows you the power of curiosity, right? That desire to uncover the universe's secrets, no matter how strange or confusing they might seem. This discovery is a perfect example of that, and a reminder that we've only scratched the surface. There's so much more out there to find.
For sure. So if today's deep dive into the quantum realm got your gears turning, if you're even a little bit fascinated by these invisible connections and particles that act up well, keep exploring. Dive into the world of quantum physics, read up on these mind-blowing experiments, and hey, who knows, maybe you'll be the one to make the next big discovery. Until next time, keep those questions coming, keep searching for answers, and never lose that curiosity about the universe and its mysteries.